Hello everyone. I hope I'm audible, right? And my screen is also visible. And if there is any problem with the visibility of screen or network issue from my side, please let me know. I'll try to fix that. And so let's start today's tutorial session. And this is going to be the last tutorial session for this course, uh, Advanced Linear Algebra. And this is actually an additional tutorial session. Okay, so and today is 13th April, right? So this is going to be the last tutorial session. So for this course. So if you have any specific doubt, please let me know. In fact, even if I'm doing any problem and in between that you need some clarity of some problem, you can let me know. I'll um, try to answer those problems. And anything which is in the course content not able to understood clearly, or any problem which I try to solve. Um, So in this tutorial, basically what I'll do, I'll try to solve problems which is mostly from the diagonalization and inner product space. And good evening. Um, mostly coming from the inner product space um, and the normal operators and the diagonalizations. I'll try to solve those problems. So let's start. If you have any problem, you can let me know. I'll try to solve this. Meanwhile, I'll start with a problem, and and I hope all the results which we have discussed, which is relevant for this tutorial, for this course, and even I will try to whatever results I am using, I will try to whatever results I am using, I will try to mention that result. Okay, so let's start with this problem. I hope my screen is clearly visible right now. If there is any problem with visibility, please let me know. Okay, so this is one of the problem. So let P be a linear operator from R9 to R9. Say here R9 is considered as a vector space of dimension n, and and R9 is considered as a vector space of dimension n over dimension 9 over the real field. Okay, and let B be a standard order basis. So what is mean by B? B is actually standard order basis, that is considering E1, E2 all the way En. Good evening. And where EI is actually the end nine tuple with only non-zero entries, with only non-zero entry 1 at ith place. That means E1 is actually 1 comma 0 0 0, like each element is consisting 8 0 and 1 1, and 1 1 will place for the E1, it is at the first place, E2 it is at the second place, E3 it is at the third place, and in this way E9 it is at the ninth place. E1 is look like this way, something like that. Okay, let W1 be the null space of A minus identity operator. So W1 is the null space of A minus identity operator, and W2 is the null space of A minus 3i square, and W3 is the null space of A minus 5 by q, where W is equals to W1 plus W2 plus W3. Just a minute. So from here, what we can say is that, so from here, what we can say there is a theorem. I will try to recall that, and we have mentioned that theorem during the regular tutorial session, and in fact it is discussed in the um main course content, that is regarding diagonalizability of a linear operator on a finite dimensional inner product vector space. That says if and here it is mentioned the minimal polynomial of t is the, so what is mentioned first, minimal polynomial of t, minimal polynomial of t, minimal polynomial of t is mx, that is equals to x minus 1, x minus 3 square, and x minus 5 cube. Okay, and so therefore what we can say is that the characteristics polynomial is that characteristics polynomial will be that is fx, that will be equals to x minus 1. As we know, characteristics polynomial and minimal polynomial must have the same root. They don't have any distinction. Okay, so if I consider d1, d2, d3 is the power, then d1 will be greater than equals to 1, d2 will be greater than equals to 2, and d3 will be greater than equals to 3. And in fact, d1 plus d2 plus d3, it has to be equals to 9. Okay, so and d1, d2, d3 are called the algebraic multiplicity of the eigenvalue 1, 3, 5 for the linear operator t. Okay, and what else we can say from here? So first question is, the first option is given. What are the options given? That geometric multiplicity of the eigenvalue 1 is 4. So that we have to see whether it is true or not. If T1 is the operator induced on W1 by T, the minimal polynomial of T1 is x1 minus 1 to 1 square, and T2 is the operator induced by W2 by T, then minimal polynomial of T2 is x minus 3 square, and T3, if T3 is the operator induced on W3 by T, then the minimal polynomial of T3 is actually x minus 5 3. So all three options has to be clearly correct. Why that is? That is due to the primary decomposition theorem. So let me state the primary decomposition theorem. So what recall that primary decomposition theorem says that, recall the primary decomposition theorem. What it says, let T be a linear operator. Let T be a linear operator on a finite dimensional vector space V, finite dimensional vector space V, and let P be the minimal polynomial. P be the minimal polynomial of T, and P actually given by P1 to the power R1 all the way Pk to the power Rk, where Pi's are distinct irreducible monic polynomial. So what was monic polynomial? Monic polynomial is a polynomial where the coefficient of the highest degree per term is actually 1. That means if xn is the degree of the polynomial of a polynomial, then it is monic polynomial if the coefficient of x to the power n is actually 1. Monic polynomials over the field F where the vector space is actually defined, and Ri are the non positive integers greater than equals to 1. So if the minimal polynomial is factored in this way, then I am coming to the what are the consequences we will have. Ri are the positive integers. Let Wi is actually the null space of Pit to the power R, for all I equals to 1 to k. Then what are the consequences I will have? That V is equals to W1 direct sum all the way Wk, because here is k situation is there. And second thing is that each Wi is invariant under T, and the third consequence is that if Ti is the operator induced on Wi by T, then the minimal polynomial minimal polynomial of t is pi to the power ri. So here is the last thing which I will be using for this last three options. So what it says, suppose we have a linear operator t on a finite dimensional vector space V defined over a field F, and let t be the minimal polynomial for the linear operator t. Then it be the minimal polynomial for the linear operator t, and p is factored like this, where each pi is actually irreducible. That means they are not possible to decompose further. Each pi is actually irreducible, distinct, irreducible monic polynomials over the field f, and Ri are some powers, positive powers. And if I consider Wi actually the null space of the operator pi to the power rt, then V has to be equal to direct sum of W and W to W2. That means each W are actually orthogonal to each other, and their sum is actually the vector space V. And each Wi is invariant under T. What was invariant? That is T of Wi is actually subset of Wi. If I take an element from Wi and apply the linear operator T, then that is going to the Wi. Now if I consider, so that means Wi is invariant. So therefore we can consider T restricted to Wi. That will be an operator from Wi to Wi. Wi is a subspace of the vector space V. Okay. Then this is a new linear operator. Now the minimal polynomial for this new linear operator is actually pi to the power ri. This is what it is. Okay. This is very important theorem for the primary decomposition theorem, because this is where the Jordan-canonical form is based on this. One of the main building blocks for the Jordan-canonical form for a linear operator T or a matrix finite square matrix A. So now, let's go back to the problem. So what second option says that if T1 is the operator induced by W1, then the minimal polynomial of T1 is x1 minus 1 square. So whether this is true, the minimal polynomial for T actually supposed to be, here as the minimal polynomial is this, then here P1 is actually P1x actually x1 minus 1, P2x is actually x minus 3, and here R1 is equals to 1, R2 is equals to 2, and P3x is actually x minus 5, where R3 is actually 3. Then the minimal polynomial of T1 has to be T minus identity, P1T, right? Because R1 is 1 here. So therefore this option is incorrect, because here it is given that x1 minus 1, x minus 1 whole square. That's not correct, right? Because actually this has to be x minus 1. Minimal polynomial has to be x minus 1, but that's not how it is given. It is given x1 minus x minus 1 square. Then the T2 is the operator induced by W2, then the minimal polynomial of T2 is actually x minus 3. That's correct, because the minimal polynomial corresponding to the subspace W2, that has to be P2 x to the power R2, and P2x equals x minus 3 and R2 is 2. So that's why this is correct options. And what is the third option? Says that if T3 is the operator induced on W3 by T, then the minimal polynomial of T3 has to be x minus 5. That is also correct due to the same reasoning and the third consequences of the primary decomposition theorem. So this is also correct. Okay. Now let's come to the first options. Whether first option is correct or not. What the first option is says that the geometric multiplicity of the eigenvalue 1 is 4. Whether this is correct or not. Okay, what is mean by geometric multiplicity? Let's recall geometric multiplicity of an eigenvalue Ci is actually the dimension of the space, that is null space, that is kernel of T minus Ci identity. That is what it is, the dimension of this space is actually the geometric multiplicity, and algebraic multiplicity is the degree of the factor x minus C in the characteristics polynomial, not the minimal polynomial. If this is the characteristic polynomial, then the algebraic multiplicity is D1. Okay. But I don't know what is D1, but D1 has to be greater than equals to 1. That's for sure, because the characteristic polynomial and minimal polynomial must have the same factor. Okay. Okay, and the characteristic polynomial should be divisible by the minimal polynomial. So therefore it will be at least D1 will be at least greater than 1. Now, geometric multiplicity of the eigenvalue 1 is it is correct or not. That need not necessarily, because I can give and create a counter example where this is not happening. Okay. 3 to 4. Okay, no, we don't need actually. We don't need. So from here, what we can say is that clearly, algebraic multiplicity of 3, that is equals to, that is second eigenvalue, that has to be at least greater than equals to 2. 2 greater than equals to 2. That is algebraic multiplicity is greater than equals to 2, and algebraic multiplicity of 5, that is also greater than equals to 3. Right? Therefore, Therefore, if d1 is the geometric multiples d1 plus d2 plus d3, so that is, this means that d2 is greater than equals to 2 and d3 is actually greater than equals to 3, and this is equals to 9 we know. So that will be equals to, that will be greater than equals to d1 plus 2 plus 3, that is equals to d1 plus 5. So that says that d1 has to be less than equals to 9 minus 5. So that is equals to 4. d1 has to be less than equals to 4, right? So if d1 is less than equals to 4, okay, it is not necessarily 2 plus 3, d1 has to be greater than equals to 1, that's true. So that means d1 has to be greater than equals to 1, that's clear, and less than equals to 4. But the algebraic multiplicity will be always less than equals to d1. So 4 can be, okay, let me give you an example. Let me give you a matrix where it is happening. Let's take A is equals to the matrix 1, 1, 0, 0, 1. This is okay, this is okay, this is okay. This is one block. Another block is 0, 1, 0, 0, and okay, no, I think one block has to be 1. Okay, one block has to be 1, because here only, okay, let me give you the matrix, that is 1, 1, this is, and let's take 3, okay, and then 3 plus 2 to 4, 4 to 7, so here you can give only 2. So, and there is another eigenvalue is 3, right? So 3, 0, 3, 3, 1, 0, 3, and 5 is the 3, 1, 0, that is 5, 1, 0, 0, 5, 1, 0, 0, 5. So clearly this is 1 plus 1, 2, 2 to 4, 4, 4 to 6, 6 to 9. This is a 9 by 9 matrix, clearly, right? I am writing here, it is as a block form, okay? So this matrix, it is clear that for this matrix, the minimal polynomial is actually x minus 1, x minus 3 square, and x minus 5 cube. But here the geometric multiplicity of 3, 1 is actually 2. Geometric multiplicity of 1 is actually 2. You can, I think if you recall the fact that whenever you have a matrix, I mean, whenever you have to find the Jordan canonical form out of a minimal polynomial or the Cash-Status polynomial, then what is, you know, that what is the power of the minimal polynomial, you have to give that square block. Okay, so for example, here the minimal polynomial is this one, x minus this one, that x minus 1, x minus 3 square, x minus 5 cube. Okay, so here if you want to, if you want to give a block corresponding to 1, as the power of x minus 1 is 1, so there will be at least one block of 1, and all other block will be power will be less than equals to 1, corresponding to 1. So therefore all other block corresponding to 1 will be less than equals to, degree will be less than equals to 1. So that means there is only block of 1 will be of 1 by 1 matrices, okay, and corresponding to 3, the block will be 2 by 2, and all other blocks corresponding to 3, that has to be less than equals to, order will be less than equals to 2, but that can be 2 also, right? So here if I can give, this is the block, so then in this case still it is satisfying all the property. In fact, one can change this little bit, this fact little bit, and one can get a new matrix where the minimal polynomial will be as it is, but the eigenvalue, but the geometric multiplicity of 1 need not be 2. Then geometric multiplicity of 1 need not be 4. So therefore the option A is incorrect. Okay, I hope first three fact is very much clear. First three what I have tried to give, that using the primary decomposition theorem, that I hope it is easy. Whether the last one is clear to everyone or anything, even in fact for the primary decomposition theorem, you can ask me. Is that problem, how I am trying to solve this problem, is clear to everyone? Okay. So if there is any doubt, very simple event that can be, you can let me know. I'll try to answer that one. Okay. So even I'm going to the next problem. If there is any doubt to you, you can stop me and ask me. I'll try to go back and try to solve that one. So this is another problem. So let's read the problem. So what this problem says, let A be the matrix 2 0 0. It is given like this way: 2 0 0 1 2 0 0 0 minus 1. So it is clear that for this matrix, this is an upper triangular matrix, right? Sorry, lower triangular matrix. That all the upper triangular entries are 0 except the diagonal. And clearly for this matrix, the minimal polynomial for this matrix, the characteristic polynomial will be x square, x minus 2 square, x plus 1, and the minimal polynomial will be itself. There is no other change. I'm going to here why this is the minimal polynomial, but okay. But what it is given, let's read what it is given. Let W1 be the null space of a plus I, and W2 is the null space of a minus 2i, and W3 is the null space of a minus 2i square. Let E1, E2, E3 be the projection operator on R3 such that W1, W2, W3 are the range space of W1, E1, E2, E3 operators respectively. Then which of the following statement is which of the following statement is or are correct? Okay. Okay, so let's start. So here the matrix A is actually given 2 0 0 1 2 0 0 0 minus 1. So let's think like this is a block matrix, like look like this way. Then it is clear that the characteristic polynomial fx, that must be equals to x minus 2 square x plus 1 and minimal polynomial. So from here it is clear that minimal polynomial will be at least x minus 2 and x plus 1. This will be at least, and as the algebraic multiplicity corresponding to the eigenvalue minus 1 is 1, so therefore in the minimal polynomial this power can't go beyond 1. Okay, so that, so and the as the algebraic multiplicity, this or this minimal polynomial will be either this or this. But why this is not the minimal polynomial, I'm going to say why this is not the minimal going to be the minimal polynomial. But this is the minimal polynomial. This can't be the minimal polynomial. Why this is not the minimal polynomial? You can check two ways. One is that you can check that a minus 2i times a plus I, that has not, that will not be equals to 0. Why? You can check a minus 2i means that will be 0 0 1 0 0 0 1 0 0 0 0 minus 1. This is the a minus 2i, and a minus I will be 2 0 0 1 2 0 and 0, sorry, this is plus, right? So this will be like 2 3 1. So here we also change, I'm subtracting 2, that will be minus 3. So if you, this is a minus 2i and a plus I. A was, recall that a was 2 0 0 1 2. You can just try to subtract 2 identity from there, you'll get the first one, and if you can subtract, you can add 1, all the diagonal entries here, identity, you'll get this. So if you multiply, this will be, first entry will be 0, second will be, this is clear. Now this entry will be non-zero. Why? You can look at carefully, 1 3, this is 3, next one will be 0, next one will be 0, and I hope all the entries will be 0 except the last one. Okay, 0, oh, this is 0. Okay, yeah, a minus 3, this is 0. So yeah, so last entry will be 0, last will be 0. So this is what it is. So this is of course not equals to 0. And why this is happening? If you remember, in the Jordan canonical form, when we are trying to find, whenever 1 is not an eigenvalue, suppose we have a power x minimal polynomial, in the minimal polynomial we have something like that x minus c to the power 3, then that there will be at least one block of 3 by 3 consisting corresponding to c, and that block is like c1 0 0 c1 0 0 c, right? So here we have this type of block, and you can't reduce this one without making it square. Without making it square, you can't reduce, you can make it 0. Okay, so here is similar block but corresponding to the 2 by 2 matrix and 1. So that's why it is not there. So clearly the minimal polynomial, you can check two way. You can use your just instinct that from the Jordan canonical form of a matrix, and where which I am saying, suppose you have this power in the minimal polynomial, you have this power, then what, at least one block in the matrix that has to be equals to this one, that is c 1 0 C1 C. This has to be at least one block in, then whatever the other block will be, that will be of order less than equals to 2. That can be of 2, but that can be of 1 as well. Okay. So here is one such block. And why these things appears? Because there is an instinction, that is that if you have a matrix like 0, 1, 0, if you square it, then it will become vanish, right? You will get like 0, 0, 0, 0. Okay. So that means for this matrix, this 0, 1, 0, 0, the minimal polynomial is x minus x square, right? So now, whenever c is the eigenvalue, then x minus c is the, suppose consider the matrix. This is something like x minus ci. That means if the minimal polynomial is this, then this matrix can't be 0. We have to make square, the corresponding block will become 0. Okay. So therefore the minimal polynomial, therefore the minimal polynomial is x minus 2 square and x plus 1, and characteristic polynomial is same, x minus 2 square and x plus 1. So then by the primary decomposition theorem, if w1 is actually equals to, if w1 is actually equals to the null space of a plus I, w1 is actually the null space of a plus I, and w2 is actually equals to the null space of a minus 2I. Okay, then we know that w1 direct sum w2, that has to be equals to the vector space V. Okay, so but here I think w3 is the null space of a minus 2I, w3 is the null space of, so it will be w2 plus w1 plus w3. So that means this option is not correct. This option is correct, and that's clear that W2 is actually the eigenspace of corresponding to the eigenvalue 2, but that eigenspace is not enough to consist to form the vector from the eigenspaces are not enough to constitute the basis of the vector space V. Okay, if it is enough, then the matrix has to be diagonalizable, but this matrix is not diagonalizable. Okay, this matrix is not diagonalizable, this is for sure. Now if I consider P is equals to minus E1 plus 2E3, then this is diagonalizable. Okay, so any matrix as E1 and E2 are look like this, as E1 is actually the projection on the W1 and E2 is the projection on W2, then there is a theorem which I have not mentioned. I mean, I have mentioned in the regular tutorial session. In fact, it is mentioned in the course content, that if there exist C1, C2, Ck distinct real number, C2 not real number, distinct complex number or distinct scalar. Scalar means they are element in the field. If it is real, then it is in real. If it is complex over, then it is over complex, then it is complex. Such that if T is equals to C1, E1 plus C2, E2 plus all the way Ck, Ek, and the satisfying the property that Ei equals to E1 plus E2 plus Ek, and this Ei actually delta Ij, that means equals to 0 if I not equals to j, and ei square is actually equals to ei, that is the projection. This is what is called projection. This is the property. And the third one is that if wi is equals to, if wi is equals to ei, sorry, wi is equals to range of ei, then w1 plus direct sum, all the they will be orthogonal, and this is equals to the vector space V. Then T is diagonalizable. Diagonalizable. Here is nothing is there. We have the fact that V is a vector space. Here there is no initial assumption. Here what we have assumed, V is a vector space, finite dimensional vector space, and let C1, C2, Ck are distinct scalars, distinct element from the field where the vector space is defined, and let us consider E1, E2, Ek are operators on the vector space V, which are satisfying the property that Ei, Ej is equals to 0 if I not equals to j, Ei square equals to Ei, that is the projection for all I, and identity operator is actually E1 plus E2 plus Ek, and T is equals to operator C1 plus C1 plus C2 E2 plus Ck, and this will automatically, I think this will automatically because of the fact that I equals to E1 plus E2 plus Ek, then T is diagonalizable. So here we have seen that if Wi is actually equals to W1 is actually range of E1, and W3 actually equals to range of E3, and E1 plus E3 is actually identity, and this is vice versa due to the fact that V is equals to W1 direct sum W2, okay, W3. Therefore therefore C1 C2 is equals to -1 and C2 is equals to 2. Therefore the operator T, here it is given by P given by minus E1 plus E2 to E3 is diagonalizable. Okay, so this is the option, right? E1 minus E2, this is diagonalizable. Instead of E3, if it is given E2, then it is not diagonalizable because E2 is actually not relevant in this situation. Okay. Now let's last options. So let T minus P is nilpotent operator of index 2. Okay, I have to check whether T minus P is nilpotent operator of index 2 or not. Okay, so T is actually T can be written. Now E1 we know what is E1 E2 E3. We have observed, we have seen here is an interesting fact. We have seen that E1 plus E3, this is equal to V, sorry, this is equal to identity operator, and correspondingly their range space, direct sum of the range space is actually E1 it is identity operator. And why this? I mean, there is many things are interrelated. It's better to understand those things because those are the essence of this course. Here many facts is there. Suppose we have E1 and EI EJ. Here EI EJ is equals to 0 if I not equals to J. That is actually related to the fact that Wi at intersection Wj, that is equals to 0. The same thing. Okay. And EI square is equals to EI, that means that is EI is actually orthogonal projection on some subspace, and that is the Wi. As we have this fact and T is the given operator, then we can write T is equals to T of E1 plus T of E3, right? And we have obtained what is P here. Now let's obtain T minus P, that is T of E1 plus T of E3 minus of E1 plus 2 of E3. Here E1, E2, E3, T all are actually the operator, right? So T plus identity whole E1 plus T minus 2I whole E3, we have this one. Now we know that T is an operator which satisfies the property that recall that minimal polynomial is actually T minus minimal polynomial is actually x minus 2 square and x plus 1. So that means that is T minus 2I whole square T plus identity, that has to be equals to 0. This is what it is the minimal polynomial represents. So therefore, if I consider T minus P square, then what I will get? T plus identity whole E1 plus T minus 2I whole E3, this whole square, right? So what I will get? This will get, I will get T plus identity whole E1 T minus 2I whole E3. Here I just want to point out that these projections actually are polynomial in T. Okay. Another is that 2 times, not 2 times, it will be actually this will be 2 times. This will turns out to be 2 times that T plus okay, I have written the T plus identity whole E1 T plus identity whole E1. Here we don't have the commutativity. And another is that T minus 2I whole E3 T plus I whole E1, and another is the T minus 2I whole E3 T minus 2I whole E3. Recall that these EIs are polynomial in T. In fact, EIs are equals to f of IT, where fi is actually suppose the minimal polynomial is x minus c1 square, x minus c2, something like that. If minimal, that will be x minus c1 to the power m1 all the way x minus c I minus 1 whole to the power m I minus 1. Okay, let me write this is clearly. If you can use this is on another problem wherever is needed. If this is in general I am writing, if mx is equals to x minus c1 whole to the power m1 all the way x minus ck whole to the power mk, then f of ix is actually x minus c1 whole to the power m1, x minus ci minus 1 whole to the power mi minus 1, x minus ci plus 1 whole to the power mi plus 1, all the way x minus ck whole to the power mk by ci minus c1, ci minus c, all the way, this will be all the ci minus ci minus 1 and ci minus ci plus 1, ci, this is superscript, sorry, this is subscript plus, this plus 1, and all the way c minus ck, ci minus ck, this is what it is. Okay, if you are not able to catch this fact, so you don't need to be pressurized in your brain, then you can leave this, but they are polynomial, you can remember that they are actually polynomial. Okay, so then fit actually the polynomial EA. So as they are polynomial, why I am recalling this fact, as they are polynomial in T, they will be commutative with respect to the operator T minus I, T plus I. So therefore, we can write this fact as T plus I whole into T minus 2I whole E1, E3. Next one will be T plus I square E1 square. Next one will be T minus 2I T plus I E1, E3. Next one will be T minus 2y square E3 square. Now recall that E1, E3 are actually 0. This is 0 and this is 0. And E1 square is actually E1 and this is equals to E3. So therefore we can write this is actually T plus, okay, I think I made a little mistake. No, I have not made a mistake. T plus I square E1 plus T minus 2y square E3. Okay. Now look at carefully. This is the matrix which is actually equals to 0. Why this is actually 0? Because t plus I, what was the t? T is actually recall the t 0 0 1 2 0 0 0 minus 1, right? And E1 is actually corresponding. E1 is actually the matrix corresponding to E1 is corresponding to minus 1. So this will be 0 0 0 0 0 0 0 0 minus 1. The matrix representation of E1 will be this one, and matrix representation of E3 will be 2 0 0 1 2 0 0 0 minus 1. Actually, matrix representation of E1 that is I think yeah, I think this is correct. I hope this is correct. Matrix representation of this, and if you replace this t plus I, that has to be 0. In fact, here I just want to say here is that suppose this is in general true. These facts are there is in fact general actually. Suppose T is a linear operator for which you have the primary decomposition theorem. So basically what we can obtain that, okay, let me say what I obtained, that T minus P actually the nilpotent matrix. T is a nilpotent matrix. And what is nilpotent matrix? A matrix is said to be nilpotent if its some power is actually going to be 0. Okay. So that means the last option is actually correct. Okay. Here is the general fact of index 2. Index 2 also mentioned, because 1 the power is not going to be 0. But here I just want to give a theorem, you can say theorem, if Px is equals to, or Mx, if Mx is equals to x minus c1 whole to the power m1 all the way x minus ck mk be the minimal polynomial of a linear operator P on a finite dimensional vector space V, then if Wi is actually equals to kernel of T minus Ci whole to the power mi for all I equals to 1 to k, then we know that by primary decomposition theorem W1 direction W2 that has to be equals to V, and if you restrict invariance, all these things will be there. But the fact is that if Ei is actually the projection onto W1, Wi, then the operator summation of Ci Ei I equals to 1 to k is diagonalizable, and P minus D its power r is actually 0, where r is actually maximum of this m1 all the way mk. This is generally true. So using this theorem, this whatever I have tried to say, using this theorem, you can directly conclude these results, that minus e1 plus 2e2 2e3 is diagonalizable, and p minus p is actually nilpotent linear operator of index 2. And this is the index diagonalizable on with index r. That is p minus d is nilpotent, sorry, not diagonalizable, nilpotent with index r. R is the smallest integer for which the power is actually going to be 0. So this will solve the complete the solution of this problem. So I hope the last one is going to create little problem in your mind, but other things should not create. I hope that is not going to be difficult. Is there any problem especially for the last options? I mean, is there any problem to understand the last options? If you are not able to understand, then at least try to remember this last whatever I've tried to say here. This is then generally true. But remember, mx has to be completely factorized this way. There should not be any degree to polynomial. Mx has to be completely factorized into linear factors, but power can be different. Okay. So is this problem clear? I mean, at least any doubt is there? Okay, I hope the last option is not easiest one. But for the last options, you can okay. For the last options, you can remember that theorem. That one, I mean, you can find it in maybe not formally it is written, but you can find it in the Hoffman-Kunz book, Linear Algebra book. But this is what it is in general too. So let me go to the next problem. These problems are today's problems are little more comparatively difficult in compared to usual, because these are the problems that nowadays problems in nowadays are not coming easily. Maybe for your exam it's okay, but if you are going to appear in the exams like NET or in JAM, then you have to be little tough problem. You have to solve little tough problem. Okay, so let me go to the next problem. What this problem says: let A be an n cross n matrix. Actually, this is there is a little problem. So let n cross n matrix, and lambda is an eigenvalue of A that is not 2 or 5. Jk denotes the Jordan block of A corresponding to the eigenvalue k, eigenvalue of order k. That means that many times it appears. Okay. Okay, so J5 means the J5 lambda means any Jn basically. Okay, let me write what is Jn. Jk lambda means this is a k by k matrix. Okay, and where the diagonal entries, all diagonal entries are lambda, this is 0, and super diagonal entries will be 1. This way, this is what it is. So this way it is going to be like. So second one will be like 0 0 0 lambda 1, last one will be 0 0 0, this one. This is what it is, jk lambda. What is mean by jk lambda is this is the jk lambda. Now let's write j5 lambda. So what is j5 lambda? That's clearly lambda 1 0 0 5 by 5 matrix, 0 lambda 1 0 0 0 0 lambda 1 0 0 0 0 lambda 1 and 0 0 0 0 lambda. This is the j5. Now j5 lambda minus lambda i5, what it will be? Lambda will be deleted from the main diagonal, so it will be like 0 1 0 0 0 0 0 1 0 0 0 0 0 0 0 0 0. Oh sorry, here it is, 1 will be there. Yeah. Interesting fact is that this type of matrix actually denotes the differential operator, right? some sense differential operator, but not completely. But that's a separate thing. But this matrix has special thing. If you consider this is a matrix, then its power, then actually its power will be A. If I consider this is the matrix A, then A5 will be 0. But A4 is not 0, and no other lower power is going to be 0. A5 is the 0. You can check. This is very interesting, and this is each time you multiply, each time you square it, this one will be shifted to the above one, shifted to the above diagonal. For example, I can give you, okay, this is some general fact. You can use this for exam. That's what I'm trying to say, that not for not this purpose. Let's take, this is a 3 by 3 matrix. This is the matrix. If you square it, this one will be shifted to here. So if you do, this is first entry will be 0, second entry is going to be 0, third entry is going to be 1, and this entry is going to be 0, 0, 0, 0, 0, 0. And if you again multiply with 0, 1, 0, 0, 0, 1, 0, 0, 0, then this will vanish. So you need that much power. This is 3 by 3 matrix, then you have to multiply 3 times, then you will get 0. Okay, so what is the question here? It is given that rank of J5 minus lambda is actually 5. So it is already in row reduced echelon form. There is no doubt about this. Okay, because each row has the leading entry 1, and if an entry is the leading entry of some if some row, then the all other entries in that column is 0. So that's why it is in row reduced form. So in row reduced form, in the row reduced form, what is the rank of a matrix? Rank of the matrix is the number of non-zero rows. So what is the number of non-zero rows? That is 4. But here it is written 5. So that's why this option is not correct. Okay. Now similarly, we have to find J4 minus 2i, 2 times i4. So J4 minus 2 times i4, that will be equals to, J4 means diagonal is corresponding to the eigenvalue J4 lambda. I think lambda it is mentioned, J4 lambda. So that will be lambda minus 2, 1, 0, lambda minus 2, 1, 0, 0, 4 matrix. So 0, 0, lambda minus 2, 0, 0, 0, so this is 1, 0, lambda minus 2. Now question is that what is the rank of this matrix? Here it is given that lambda is neither 2 nor 5. So that means this lambda minus 2 is not going to be 0. And here even it is becoming 0, there is 1 to do something. So therefore, the rank of this matrix, rank is actually 4. So this option is correct then. J5 minus lambda 5 whole 3, whole to the power 3. Here it is the thing which I have tried to mention here. J5 minus lambda 5, I have mentioned the matrix. J5 lambda minus lambda 5, lambda I5, that is equals to 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. So this is the matrix. Now if I consider this is the matrix A, if you do A square, then this row will shifted to here. Okay, you can check. I'm not going to that one. I'm going to write that one. Check that one. You can check that one. Now if you multiply A cube, that means that is equals to A square into A. This row will shifted to the above. So that will be like 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0. This one, yeah. So that means what is the rank now? Rank is 2, right? So rank is actually 2. So what are the options? This is correct option then. Now rank of I3. Then that's also similarly J4 minus 5i. Or J4. Okay, that I'm going to discuss. Okay. J4 minus 5i4. So what is the J4 minus 5i4? J4 lambda minus 5i4, that is equals to lambda minus 4, 1, 0, 0, 0, lambda minus 4, 0, 0, 0, 0. So this is 1. But here this lambda is actually lambda minus lambda 4. Okay, this is 5, not 4. So therefore lambda minus 5 is not 0 as lambda is not equals to 2 or 5. So here you don't have the privilege which you got here above, that if you multiply it once again, that this one thing will be shifted to above. That privilege is not possible to here. In fact, if you that lambda minus 5, let's do once, at least once. 0 minus lambda 5 1 0 0 0 lambda minus 5 once 0 0 0 0. So if you do the first row, what is the first row? That is lambda minus 5 square. Okay, forget about whatever is there. I don't know what is there. Let's do this, and let's do this. What is the 2 entry? 2 entry is actually second row and second column. If you multiply second row and second column, what you will get? 0 0 lambda minus 5 0. That will be lambda minus 5 square. And whatever is there, I am not worried about. This way, you will get all the diagonal entries will be lambda minus 5 square, like this way. So whatever it is there, it does not matter. In the each diagonal entry, you get lambda minus 5 square. Okay, this is what you will get. Now if you do 3 times, you will get 3 here. If you get 3 times, you will get if you multiply it 3 times, you will get 3 here, whatever is there. But actually, in fact, it will be upper triangular matrix. That is what it is using here. It will be upper triangular matrix. Let us calculate the first entry. That will be like second row, second one. That will be 0. You can look at carefully. That will be 0 0 0 0 0. This is what it is. Whatever is above, I am not worried about this. Okay, this is upper triangular matrix. So similarly, if you take, this is the matrix A here, this is the matrix A here, then whatever power you can do A n, that will be lambda minus 5 n, some non term that can be non-zero, 0 doesn't matter. This is 0, this is 0, lambda minus 5n, this is non-zero term, this will be 0 0 lambda minus 5n, some term 0 0 lambda minus 5n. This is the pattern. So that means whatever is there doesn't matter. Here the number of non-zero row is actually 4. Whatever power you take, that doesn't matter. Number of non-zero, and if you do the row reduction process, still you can't make this term 0. You can't make this term 0. Whatever you do doesn't matter. You can't make this term 0. Okay, in the row reduction, non-zero row is 4. So therefore, rank is actually 4. But what is the option it is given? Rank is 1. So that's why it is not the correct option. Is this problem clear? I don't know. This is not. I am supposed to. This is something calculation is there, but I am not doing the calculation clearly. But these are you should check these calculations by your hand, at least for the some of them, and you will get the whatever pattern I have tried to set. That pattern will be visible to you. Okay. So if there is any doubt to anyone, so you just stop me and I will try to. Even I am going to the next problem, that time also you can stop me and try to ask me. I'll try to explain that problem. What is this problem says? Let V be the space of all polynomial functions fx over C such that the degree of fx is 4. So whenever consider V is a polynomial function space over the complex field and degree is considering 4, so that means V is a vector space of dimension 5, because those are actually 1x, x square, x to the power, x cube, x4. Okay, so that is V, dimension of V is actually equals to 5, and 1x, x square, x cube, x to the power 4 is an ordered basis. Need not be orthonormal. Orthonormal, we need the inner product. There is no inner product right now. Ordered basis. Okay. Let D be the differential operator on A. So then let A be the matrix of D with respect to the standard ordered basis of V. D be the operator from V to V. What it is that D maps P at the point x is actually P dash x. That is the derivative of x with respect to the variable x of V. Okay. Now, if we do D with 1 at the point x, so what will be? That is 0. D with x, that will be 1. D with x square, that will be equals to 2 times x. D with x cube, that will be equals to 3 times x square. and D with x4, that will be equals to 4 times x cube. So the matrix representation of D with respect to this is called standard order basis. Not only order basis, this is called standard order basis. Then matrix representation of this D with respect to beta is actually, if you look at carefully, 0, 0, 0, 0, 0, 5 by 5 matrix. This is, yeah. So 0, 1, no, this is 1 is first, 1, 0, 0, 0, 0, 0, 2, 0, 0, 0, 0, 0, 3, 0, 0, 0, 0, 0, 4, 0. So this is the matrix. So here is, if you look at carefully, the matrix which I have tried to discuss in the previous problem, this is the same matrix. Just only in the place of 1, 1, 1, here is the 2, 2, 3, 4. This is what it is, right? That doesn't matter. You can do things that B matrix, this matrix B, if you take its 4 power, then no 4 power, this will be 5 power, then 5 power will be 0, but B with B, whatever power you can take, I, that is not equals to 0 for I less than equals to 4. If you take I is 1, still it is not going to be 0, I2, I is 1 is not 0, that's clear, I2 still it is not going to be 0, I3 not going to be 0, I4, yeah, any doubt? Sahid, you have any doubt? Okay. So whatever power you can do, that doesn't matter, because you can look at basically what is when you do the first time square. So this non-zero term is going to shift here. Okay, you do the second time, this non-zero term going to be here. Okay, that means right now 3 power is came. If you do the once again multiply, that is 4th power, you will going to be here. Okay, here is the non-zero term will appear, but if you do the 5th one, that will vanish. This is the pattern. So I don't so this is so what now, let's see what is the options is there. A is nilpotent. This is the what it is called A. Okay, A is nilpotent, that's true, because A power is actually 0. You can check that one, and in fact this fact is true. If you have this type of things, this fact is true. Its pattern is something like that. A is nilpotent, that's true, with the index 5. In fact, index is 5. There is no power, lowest power, for which this is going to be 0. A is not diagonalizable. So as the minimal polynomial of A is x to the power 5, then it can't be diagonalizable, because recall that one fact, diagonalizable if and only if, I'm not writing the full statement, if and only if the minimal polynomial is actually product of distinct factor, is product of distinct factor, distinct linear factor, not only distinct linear factors, that has to be. So here, why the minimal polynomial of A is x to the power 5? Because A, the matrix satisfying this equation, x to the power 5 equals to 0, but there is no lower power that going to be 0. So that means this is the minimal polynomial, and it is clear from here the only eigenvalue of this matrix is actually 0. So the minimal polynomial A is not diagonalizable. This fact is true. I have to find the correct options. A is nilpotent, that is true. A is not diagonalizable, that is true. Rank of A is 3. That is not, of course, not true, because rank of A is 4. This is not true. Rank of A is equals to 4. The Jordan canonical form for this matrix is this, that is also not true. Because whenever you have the minimal polynomial, here the minimal polynomial is 5. Sorry, minimal polynomial is x to the power 5. Then the Jordan canonical form it should have at least one block of 5 by 5 order, that it itself J5 of the 0, that is equals to 0 1 0 0 0 0 0 1 0 0. This is the Jordan canonical form. So this Jordan canonical form has, there is a 3 term is 1, but last term is not giving 1. So that means this option is also not correct. So is this problem clear to everyone? Okay. So if there is any doubt, this is simplest problem. I think this is one of the simple problem, but not difficult. The previous one is little complication was there, but okay. I hope this is clear. If there is a doubt, you can let me know. Just 1 second. No. Okay. So let me go to the next problem. This problem will take time. This is regarding the singular value decomposition. So singular value decomposition says that actually if you have a matrix, m by n matrix, so I have tried to, in the last class I have tried to explain singular value decomposition, but I made many chaos and not able to clearly mention. If A be an m by n matrix, that here m can be bigger than n or n can be bigger than m, that doesn't matter, m by n matrix, then there exist uh, unitary matrices. Whenever it is in real field, this unitary matrix will be orthogonal only. Unitary matrix U of order m by m and V of order n by n, such and a diagonal matrix D, which is actually equals to lambda 1. This is n by n, so there it depends on, here is the lambda 1. If m is less than, this will be m by n matrix, right? Okay. So if m is less than equals to m, if m is less than equals to n, then this will be lambda 1, lambda 2, lambda m, and this here will be some 0. This is m by m less than n, so there will be more column than more rows. Okay. And otherwise, if n is less than equals to m, this will be lambda 1 all the way lambda n. This is the smallest one, and there will be 0. This is the matrix. Okay. And this lambda I has some special form. This lambda 1, lambda 2 all the way lambda whatever is the minimum, some k, where k is equals to, if k is equals to um, minimum of n and m, then lambda 1, lambda 2, lambda k, lambda 1 square, lambda 2 square, lambda square are actually are non-zero eigenvalues, or eigenvalues you can say, are eigenvalues of A star A. Now A star A is actually n by m matrix, right? But it will have the non-zero eigenvalue then, are non-zero eigenvalues, or you can say the non-negative eigenvalue, non-zero eigenvalues actually it will be. So, we have to, here what we have to ask, we have to find the matrix A, matrix C, D, U, V. D is not needed, but D is needed. You can't obtain U and V without D. So there is a two way. I am doing one way, okay, and I mean two way one can find the what is called the singular value decomposition. So what we have here, the matrix A is given. Let's see 2 2 2 3 minus 2. So now if you take A star, that will be like 3, 2, 2, 2, 3, minus 2. So A star, that is equals to, it will be 3, 2, 2, this is 3, 3, 9 plus 4, 13 plus 17, and this will be 3, 2, 6 plus 6, 12 minus 4, that is 8. This will be 2, 3, 6 plus 6 minus 4, that is 8. 2, 3, 6 plus 6, 2 plus minus 4, that is 8. Next one will be like 17. So clearly, yes, yes. Hmm. Yeah, yeah, I have just reversed the things. Just let me know what you are saying. Just go ahead. Go ahead. What you are saying. Huh. Huh. Square root you are saying, right? Yeah, actually, I have changed. Look at carefully. Actually, maybe in the last class I have tried to write square root. That time I have obtained that lambda 1, lambda 2, lambda k are eigenvalue of A star. Here I have taken lambda 1 square, lambda 2 square, lambda k square, eigenvalue of A star. I mean, you have to obtain A star A and consider the square root. Here I have not seen that lambda 1, lambda 2, lambda m or something. Here I have said lambda 1 square, this square, lambda k. Okay, na? Yeah. I mean, maybe I have just changed things. And here always it will be positive because A star is actually a positive operator, self-adjoint, the positive self-adjoint operator. So that's why all the eigenvalues has to be positive. Okay. So for this matrix, what is the eigenvalues of this matrix? Eigenvalues of this matrix is actually, you can look at carefully that eigenvalues of this matrix will be x minus 17 square minus x minus 8 square. This is the minimal polynomial. I mean, characteristic polynomial, not minimal polynomial. It will transfer to characteristic polynomial, not of A. A does not have any characteristic polynomial right now because A is a m by n matrix that need not be square matrix, and whenever it is not a square matrix, there is no guarantee, nothing like the characteristic polynomial. But A star A is a, or A star, that they are square matrix. So that's why there is something called eigenvalues making sense. Whenever A is given, A can be non-square matrix. So whenever it is non-square, there is no terms like eigenvalue. Characteristic polynomial of A star, not A star, A star. So this can be written as x minus 17 minus 8 and x minus 17 plus 8, and this is going to be x minus 25, and this is going to be x minus 9. And it's clear that the eigenvalues are 25 and 9. So then lambda 1 is actually square root of 25 and lambda 2 is actually square root of 9. These are lambda 1 square, lambda 2 square. Okay, that is actually 5 and 3, positive square root always. Okay, this is 5 and 3. So up to this point, I think we have tried. We have one problem is there where it was asked to find the diagonal matrix. So this is the diagonal matrix. So as in this case, m equals to 3, m equals to 2, and n equals to 3. Here the matrix is given 2 by 3. Sorry, m equals to row 2, m equals to 2. That means m is less than equals to 3. So here the matrix D will be 5, 0, 0, 3. This will be m by n, 0, 0. That means this is the case where m is less than n. This is the first case. But if n is less than n, we have to be the second case. This is what it is. But the main fact is that we have to find the diagonal matrix. So there is a theorem. I'm not going to use that theorem or anything. I'm just going to find how one can remember, at least try to. So here we have to find the matrix A is equals to U, D, V. We obtain what is V, D, and U and V are actually the unitary matrices. But if we are trying to find A star, so what is A star A then? UDV into UDV whole star, and we know AB for two matrix AB star is equals to, or basically I can write T1 T2 T2 star T1 star. That will be reverse. So therefore UDV V star D star U. Okay, D is diagonal and positive matrix, so therefore D star is D itself. Okay. No, D is not diagonal. D is actually not diagonal. D is actually non-square matrix. D look like this way. So if you write D and D star, that is right now, that is 5 0 0 0 3 0, and next one is the 5 0 0 0 3 0, and 0. I think this is all. So this will be carefully look at. This is 25 and this is going to be 0. This is 0. This is 9. Okay, so D star is what it is we obtain. but V is unitary matrix. So V is unitary matrix means V star is identity. So therefore this will be U, D star, here is U star, U star. So therefore what we obtain that U into whatever the matrix that is 25, 0, 0, 9, this is U star. So now A star, this is clearly this A star, this is a self-adjoint operator, self-adjoint matrix of order 2. That is, this is normal, and whenever it is normal, A star is diagonalizable. That means there exists a matrix P such that P inverse A star P is actually equals to there exists an unitary matrix. There is an unitary matrix. Why this unitary matrix that I am going to let? There exists an unitary matrix. In fact, that has to be unique. Unitary matrix P such that P inverse A star P that is equals to the matrix D star. So that means this A star is equals to P D star into P inverse. But P is unitary matrix, so that means P star is actually equal to P inverse. So this is actually going to be P D star P star. Moreover, if you remember the initial diagonalization thing for the whenever we are not reading inner product, so in that case, what was the matrix P here? P is actually the matrix consisting. So it is diagonalizable. Right now our target is not A. Our target is A star. Okay. Now A star is diagonalizable. Now whenever you have a matrix diagonalizable, that means by definition you have a basis consisting eigenvectors, right? And whenever consisting eigenvectors. Now if you take those eigenvectors and write one by one as a column vector, if you consider those eigenvectors as a column vector and write one by one, here right now A star is square matrix. I am completely dealing with square matrix right now. So if you take all the eigenvectors corresponding to that matrix, which consists the basis for the vector space wherever it is defined, then and write the eigenvectors one by one, then that is the matrix P, the matrix consisting eigenvectors which constitutes which spans the vector space basically, which constitutes basis of the vector space of C2 here. Here is the vector space C2 because A star is actually 2 by 2 matrix. That is actually as an operator from the 2 by. But whenever it is normal, so in that case, this matrix is not only the eigenvectors, they are orthonormal eigenvectors. If you remember, we had one theorem that if you have a normal matrix, there exists an orthonormal basis consisting eigenvectors. This is what it is. Diagonalizable if and only if there exists a normal matrix is diagonalizable if and only with normal operator or matrix on a finite dimensional vector space. It is diagonalizable if and only it constitutes a orthonormal basis consisting orthonormal basis. Okay, there exists a basis consisting orthonormal vectors basically. It has an orthonormal basis basically. Okay, so so that's why the matrix P is no longer invertible only, but P is actually unitary. Okay, I hope you were able to connect the things. Whenever we are in without inner product space, the matrix is diagonalizable. The matrix P, which is actually multiplying pre and post multiplying P inverse P, that was actually the matrix where the columns are the eigenvectors. And whenever you are in normal inner product you have, and you have the normal matrix or the normal operator, then actually P is actually the consisting the P actually matrix where each columns are actually the orthonormal eigenvectors corresponding to that operator or something. So that's why I'm suddenly going to the normal things. So here the U matrix is actually that P matrix. So how one will get the matrix P? Now P is something if you can obtain the eigenvectors, orthonormal eigenvectors corresponding to this operator A star, then we are done. So what was A star basically? A star is actually equal to 17, 8, 8, 17. So let's try to find, and what are the eigenvalue of this? eigenvalue is actually 25 and 9. Okay, so now a star minus 25i, and let's take this is the x1 x2, that is equals to 17 minus 25. What is 17 minus 25? It is minus 8. Minus 8, 8, 8 minus 8, x1, this is going to be 0. I'm trying to find x1 x2 basically. I'm doing the calculation directly, not going to. So it will be 8x1 plus 8x2. This will be 8x1 minus 8x2, and this is going to be give you that x1 is equals to x2. So what is the best possible choice of the vector? So one vector you can take u1 is equals not u1. I'm finding u1. U1 is equals to 1 1. Yeah. So what is, so that another one let's obtain. So what is the orthogonalization of this? That we can consider u1 is actually 1 by square root of 2. I need orthonormal. So that means norm of this has to be 1. That's why I'm taking u1. Take, okay. Now let's obtain corresponding to the eigenvalue 5. Sorry, 9. A star minus 9 identity whole x1 x2, that is equals to, if we remove 9 from 7, that will be 8. So that is once again 8. Okay, good. 9, 8. Okay, I will not get any other vector. Why? Okay, 8, 8, 8, 8. We are getting separate vector, not a problem. X1, X2, that going to give you that X1 plus X2 is equals to 0. So therefore, you have to take U2 is equals to square root of 1, 1 minus 1. And clearly, look at U1, U2 are orthonormal basis of the C2. Therefore, U equals to U1, U2. That is equals to 1 by square root of 1, 1, 1 minus 1. We can change first column, second column. There is no harm to considering this. But we have to maintain the order. So first order is 25. So that's why the first I have to consider 25. So that's why it is the order. This is the order. So let's see which option is going to. Okay, we have square root of unity. So therefore, oh god, all the options for u is giving the same thing. So that means we have not done anything basically. I mean, these are the in general. This is there, but I have to find the vector space, the matrix V. Okay, let me obtain the matrix V basically. So I mean, this is not decider. This is not the decider. This is naturally it is coming. Okay. So now we have to find the vector space V. Now let's take just a minute. How to obtain the other two? I mean, other matrix V. If you can obtain an orthogonal vector, that is enough. So there is the way that AV if AV is equals to x1 all the way. Note that A is actually, in general I am writing A is equals to m by n and V is actually n by n. So AV will be m by n. So if this one equals to, that means there will be x1, x2 all the way. This is m by n. So x n number of column. If AV is equals to this, where the columns, these are the columns basically, columns, then what we obtain that A star V. So basically I have to obtain, okay, A star V, A star AV, V star this is going to be diagonal matrix. This one is actually the diagonal matrix. V is actually right now n by n. Here m is equals to 2 and n is equals to 3. So therefore this will be 3 by 3 matrix. So this will be like 25 D star D, 25 0. This will be 3 by 3 matrix, 0 0. This is so this is what it is going to be. Okay. I have to obtain V basically, right? Now this is right now m is actually less than 2. M is actually less than n. N is 3. There is 3 vector. Okay. If AB is equals whatever it is, if we have AB and V star, A star, AB, this is also diagonalizable, and the matrix, this is diagonalizable because basically this is not diagonalizable. A star A, we have done whatever in terms of A star, but A star A is also diagonalizable. So this is also, and A star A and A star have same non-zero eigenvalue. So that means if V is the matrix of consisting some orthonormal basis, then V star A star A V, that has to be diagonal matrix, but A star it has the two eigenvalue, that is 25 and 9, but right now this has to be 3 by 3 matrix. So therefore the corresponding diagonal matrix has to be this one, because A star and A star A, they should have the same non-zero eigenvalue, exactly same non-zero eigenvalue. This is something you can generally prove. This is some general fact. Okay, so now I have to find AB basically. I have to find AB, then I can do AB, but from there. But so from here, and this is equals to, now if A is equals to U D, that matrix D, V, U D V, right? Diagonal U D V, it is U D V star. U D V star, then A star A, that has to be equals to V D star U star U D V star. So once again, U star U is actually going to be 0, and V D star D, that is going to be the matrix 25 0 0 9 and V star. So basically what we can obtain, that V star S star A V is actually equals to 25 0 0 9. So here I made mistake then. Yeah. Right now V is actually, oh, there is a V transpose. There is a V transpose. So that means I have made a little mistake here. It is okay. That is the Jordan. There is V transpose n by n. That has to be n by n. That doesn't matter. The transpose, this is adjoint actually. One second. This is 2 by 2. This is 3 by 3. Okay. No, this is what it is. Okay. V is 3 by 3, and this is the matrix. I think this is the point where I made a mistake. This is 0 0 0 0 0 0, and this is V star. So this will be 0 0 0 0 0. You have to switch make it square basically. Okay. So now from here, and this is actually equals to what was u. U is actually whatever is there, and that has to be equals to ud. This is what it is. So now from here, what will get that AB actually equals to UD. We know A, we know U, we know D. We have to find the V. Okay. So AB is equals to U is actually equals to 1 by square root of T, 1, 1, 1 minus 1, and D is actually equals to D right now I have to consider this is 2 by 2, this is 2 by 3 matrix. D is actually consider, okay, I have done extra thing basically. 25,0,0,0,90, this is what it is. 2 by 2, this is what it is. This will be 1 by square root of 3. This is 25, this is 9, this is going to be 0, this is going to be 25 into minus 9, 0. So AB is actually going to be this matrix. A is actually 2 by 3. AB is actually going to be this matrix. So now let me. So that means if you consider the columns of the vector V is actually V1, V2, that has to be equals to columns of this okay. So V can be written as equals to A star what we obtained. A star A is equals to something. Okay. A star, what we obtained, A star is equals to this matrix. Okay, that's okay. A star is equals to 17, 8, 8, 17. So now if we multiply and A star A, I can directly do, but I mean directly we have to do something. We don't need to do anything. And A star A AB is equals to UD, there is no problem. And can we use this fact, then we can do. Okay, just a minute. V is 3 by 3 matrix and A is actually 2 by 3 matrix. So A is actually equals to 3, 2, 3, 2, 2, 2, 2, 3, minus 2. This one with V11, V12, V13, V21, V22, V23, V31, V32, V33. This one is equals to something given by 1 by square root of 25, 25, 9, minus 9, 0, 0. This is what it is given. So if I multiply A transpose that side, so okay, so basically what we'll have, okay, so from here one can also write V transpose A transpose, this is diagonal, so star is doesn't matter, same thing, is equals to 1 by square root of 225 9 25 minus 9 0. So now if I multiply V transpose with A transpose A, A transpose I have to multiply from, I have to use this one or this one. So I have to obtain V transpose, right? So I can multiply A from this side and I will get 1 by square root of T 2 25. Okay, okay, yeah. This way I think this way it is going to be. So V transpose is equal A transpose A is equals to 1 by square root of 2 25 9 0 25 minus 9 0 with A transpose, that is 3 2 3 2 A transpose A I have multiplied 3 2 2 2 3 minus 2, and this is going to be equals to V transpose into this is going to be equals to A star A, actually 25 1 by square root of 2 25 9 0 25 minus 9 0, yeah, this is equals to this one, whatever it is. So from here, okay, so let me write this one. There is another formula that E A V I, that is equals to, from here you can get, I think from here you can get A V I, sorry, from here you can get that Vi is actually equals to 1 by square root of whatever there it is. I am trying to find this one. Square root of this will be V1 will be equals to 1 square root of 5 25 5 into the matrix 2 3 2 2 2 3 minus 2 and the vector 1 by square root of 2 1 by square root of 2. Okay, let me how one will get. We have AB is equals to something UD. Okay, I want to obtain rows. Okay, so this is the formula. I think you just right now use this formula right now. That's that if you have the eigenvalue, right now eigenvalues are like lambda 1, lambda 2. We have these two. Then V1 will be equals to 1 by lambda 1 with A star U1, and V2 will be equals to 1 by lambda A star U2 and V3. So here you will get the V1 lambda 2. This way you will get, here it will be like, here it will be this will be by, after calculation it will be 1 by 5 1 by 5 1 by 5. I'll try to put argument later, not a problem. I'll try to give the argument here, it is in the uploaded PDF. I'll try to give the argument here. And similarly V2 will be 1 by 3 3 2 2 2 3 minus 2, and this will be 1 by square root 1 by minus 1 by square root of 2, and this is going to be equals to 1 by square root of 2 1 by square root of 2 and 0, and this is going to be equals to 1 by square root of 18 1 by square root of 18 1 by square root of 18. This is minus 1 by square root of 18. This is what it is. Now now we have to find, we got two vectors right now, v1 v2. I need the another column vector. So for that column vector, if you look at carefully, here is so another column vector. How one will get that, here is a 0, here is non-zero, so this position is fixed. Here is plus minus this one. So let's take 1 0 0. So let's see whether this is inner product with this is going to be 0 or not. This is not going to be 0. This is not going to be 0. Minus 1. Minus 1. This is going to be 0 here, but this is not going to be 0 there. I need another vector e3 such that which is orthogonal to this. Okay. So let me find another vector. Let x1, x2, x3, this is a vector in C3 such that x is equals to, such that inner product x with the v1 is equals to 0, which is equals to inner product of x v2. So I have to find x1, x2. So what we obtain, 1 by square root of 2 x1 plus 1 by square root of 2 x2 is equals to 0. Another is 1 by square root of 18 x1 plus 1 by square root of minus 1 by square root of 18 x2 plus 1 by square root of 18 x3, that is going to be 0. So basically from here we will get x1 plus x2 is equals to 0, x1 minus x2 plus x3 is going to be 0. So so if you add these two, so what will get, 2x1 x3 going to be 0. So x1 is if you x3 is actually equals to minus 2x1, and from here you will get that x2 is equals to minus x1. So if you consider x1 is equals to 1, so x2 has to be equals to minus 1 and x3 has to be equals to minus 2, and therefore the vector x1, x2, x3, v3 is actually equals to 1 by square root of x1 square plus x2 square plus x3 square, because I need the orthonormalization. So this will be equals to, this is 1 plus 1 plus 4, that is 6. That is 1 by square root of 6. Square root of 6, this will be like, this will be like 2x1 plus x3 equals to 0, x3 equals to minus 2x1, x1 plus x2 is going to be 0. This is okay. So this will be like 1 minus 1 minus 2. This is the vector. Now look at carefully, this vector is actually orthogonal to the first vector, because orthogonal to the first vector, that's very much clear, and orthogonal to the second vector because 1 by, you can write square root of 8 plus 1 by square root of 8 minus 2 by 1 square root. So this is orthogonal. This is orthogonal. So therefore the vector v has to be equals to, the operator v has to be equals to 1 by square root of 2, 1 by square root of 2, 0, 1 by square root of 18, minus 1 by square root of 18, and 1 by square root of 18, and last one is that 1 by square root of 6 minus 1 by square root of 6 minus 2 by square root of 6. This is the matrix, and here I will give the argument. I'll try to add the argument here why I am going to take this one. Okay, because if I take start here, then I will not going to be go ahead. So I'll try to put argument in the PDF format. So let's go to another problem. Let's see whether this is what it is giving. Okay, so let's see, this is the problem. This is another problem. So what this problem says, let V be a finite dimensional linear product space over C2. So C2 means that, two tuple, finite dimensional linear product space over complex, and let U be a linear operator on V. Okay, then which of the following statement is true? U is unitary operator if and only if norm of U alpha is equals to alpha for all alpha belongs to V. This is not true. Sorry, this is true. Finite dimensional linear product, this is true, because let V be a finite dimensional linear product space, then V is a finite dimensional linear product space, then a bounded linear operator, then a linear operator P U from V to V is unitary if U alpha with U beta is actually basically we know this is the unitary if and only if U star U is equals to U star. So now here, as we are in the finite dimensional linear product space, whatever the operator you choose, it always exists the adjoint. Okay, unitary if and only this is equals to identity. Now, if you just use this fact, then for any vector, for any alpha in the vector space V, then u star u alpha with inner product alpha, that has to be equals to inner product alpha alpha, because this is I here. So that means u alpha with u alpha, that has to be equals to inner product of alpha alpha, that is equals to norm of u alpha square, that is equals to norm of alpha square, that is equals to norm of u alpha is equals to norm of alpha. So therefore, if u is an unitary operator, then we have this one. But whether if we have this fact, then whether u is an unitary operator or not. Okay, this fact is true. Why this fact is true? Because if you have unitary operator, I mean if you have an operator u from the vector space V to V, such that u alpha norm of u alpha is equals to norm of alpha, then u is actually u is actually what is called u is actually injective. Why is injective? As if u alpha is equals to 0, that implies that norm of u alpha has to be 0, that implies that norm of alpha has to be 0, and that should imply that alpha has to be 0. That is injective. And u is an operator from V to V on a finite dimensional vector space. Then u is bijective. Okay. Now u is invertible. Now we know if u is invertible, then u is invertible. Okay, let B be the matrix which is inverse. Bu is equals to ub. This is equals to identity. B be the inverse. So then we need to show that B is actually u star. How will show? So B of alpha with some B of alpha beta. If I take alpha is a vector and beta is another vector, alpha beta two vector in the vector space V, or xy two vectors in the vector space V, then B of xy, B of xy, we can take here something u star y. I can take this one. That has to be equals to ub xy, right? Because adjoint is exist. Now what is ub? Ub is equals to identity. That has to be equals to xy, right? Now we can use, I have to use that bx u star y is equals to u star y. Now u star x comma uy, that has to be equals to, why this is equals, because this was, we can write x comma y, okay, and this can be written as x u star uy, that has to be equals to 0. And why this is happening? Because already know that ux norm of ux square is equals to norm of x square. That will give that ux inner product ux, that is equals to inner product xx, and this is what it is giving, that x u star u x is equals to norm of xx. And here by using polarization, but I can't use polarization, right? I can't use polarization. So this problem, u star x, we can't use polarization. Without polarization, how one can get? Here we can one fact from here. If we have this fact, if u alpha norm of is equals to norm of alpha, then we can say that u star u alpha comma alpha inner product, that has to be equals to inner product alpha alpha. That's for sure, because we can get norm of u alpha square is equals to norm of alpha square, and that will give that inner product of u alpha is equals to inner product of alpha alpha. That will get. But here is the polarization is there, and from here we can use, here from here actually there is the polarization. that we can use that u star u alpha comma beta is actually equals to u that is equals to alpha comma beta. Okay, so let me give you the polarization identity. So what is the polarization here? Is just polarization is that if you have norm, then inner product polarization polarization. Yeah, so polarization is actually equals to, this is equals to 1 by, actually this is polarization I am using. So polarization says that polarization identity that says that for any two vector alpha beta, inner product alpha beta is equals to 1 by 4 norm of alpha beta square if it is in complex field, 1 by 4 norm of alpha minus beta square plus 1 by 4 I norm of alpha plus I beta square minus I by 4 norm of alpha minus I beta square. That is the polarization identity. And using that you can get this one, but I need to get directly. If I want to get, if I have this one, then I want to get that A star, I want to get that U star for all alpha, then I want to get that U star U beta alpha beta is equals to alpha beta. This is what I want to get. Okay, let's do that. This is, I think that will be the end then. So for any alpha beta, we know that for any vector x, or basically here I can change it. This is something very standard thing actually. This is something little standard. This is maybe not not your. So what we can get, u star u x plus iy whole x plus iy. This is going to be equals to inner product of x plus iy with inner product of x plus iy. So this is going to be inner product xx plus x with I, that will be minus I xy plus I yx plus I will came two times, but I will came minus, I will came minus I square. This one, so that is equals to yy, inner product yy, and similarly we get this one. Okay, and here left hand side I will get u star u, or basically ux, you can take ux with ux plus you will get ux equals to minus of I ux uy plus I uy ux plus uy. You can take, and we know that norm of ux is equal to norm of x square. So this will be cancelled out. This will be cancelled out. So what I will get right now? I will get I cancel out if I do, then ux uy, that is plus, this is minus plus uy ux, that is equals to inner product xy minus plus inner product yx. So here what we have used, we used ux uy, sorry, we used ux inner product is actually equals to norm of x square, that is equals to inner product xx. Okay, similarly if you use that u of x plus y comma u of x plus y, that is equals to inner product of x plus y comma x plus y, then we will get right hand side x inner product plus inner product x plus x comma y plus inner product y comma x plus inner product y comma y, and left hand side will get ux inner product plus ux uy inner product and uy ux and inner product, and another is that uy uy. Similarly, if we use ux is equals to norm of x square, uy equals to norm of y square, then what will get that ux comma uy plus uy comma ux, that is equals to inner product xy plus inner product yx. So let's give, this is 1 and this is 2. So if you add 1 plus 2, what we'll get, this will be cancelled out. Note that this will be cancelled out with this. So I will get uy with ux, that is equals to, here x inner product xy minus x, that will cancel out, and this will be yx. So basically we have started with any xy and we have obtained it. That is, for any alpha beta in the vector space V, u alpha u beta is equals to alpha beta. I have not used any polarization identity, so that's why I'm not using this one. I'm directly tried to obtain this one. This is very high technique. Actually, this is a good technique. How to get from, we initially recall that initially we had the fact that u alpha is equals to net product of alpha for all alpha. Using this fact, we have obtained that u alpha equals to this. So this will give me that u star u alpha beta, this is equals to inner product alpha beta, and also this is giving me that u star beta alpha is actually equals to alpha beta. So these two will give me that u star u is equals to identity is equals to u star. So that is u is unitary. So this will give the first answer. Now let's get to the second option. If u is a unitary operator and lambda is an eigenvalue of u, then mod of lambda is equals to 1. These are all standard things. If u from the vector space V to V is unitary, lambda is an eigenvalue, then mod of lambda equals to 1. This is what I have to prove. So just a minute. Okay, so here if lambda is an eigenvalue, of u, that means there exists a vector alpha in the vector space V such that u alpha is equals to lambda alpha, and alpha is not equals to 0 because eigenvector can't be 0. But we know that u alpha norm square is equals to norm of alpha square. But u alpha is equals to mod of norm of lambda alpha square. But that means norm of alpha square is equals to mod of lambda alpha norm this square. And this is equals to mod lambda into norm of alpha square. Now norm of alpha square is equals to not equals to 0. Therefore mod of lambda equals to 1. So that means what you will obtain, unitary matrices, all the eigenvalue of unitary matrices is actually of modulus 1. What was the third option? So second option is actually correct. I think here all the options are correct. I have tried to construct these questions, just taking all the questions from the Hofmann-Kunz and try to give the new questions. If u is a unitary operator, then the operator s equals to u plus u star is self-adjoint and all its eigenvalues are real numbers lying in the closed interval minus 2 to 2. This is very difficult questions. For the third options. So what is given? That u is an unitary operator, and s is equals to u plus u star. If lambda is an eigenvalue, here is one first fact, lambda is an eigenvalue of note that, okay, first note that s is self-adjoint. S is self-adjoint. Okay, that is s of x, s star, this is s star, which is equals to u plus u star whole star, that is going to be u star plus u. Okay, so that is again s, so s is self-adjoint. So then all the eigenvalues of s must be real. This is one fact. Now if lambda is an eigenvalue, so I have to prove that if lambda is an eigenvalue of u, then there exists a vector alpha in V such that u alpha is equals to lambda alpha. Now u is a normal operator, and we know for a normal operator, if lambda is an eigenvalue alpha is an eigenvector corresponding to the eigenvalue lambda of the operator t, then alpha is actually the eigenvector corresponding to the eigenvalue lambda bar. Okay, then lambda bar is an eigenvalue of u star corresponding to the with the eigenvector v, with the eigenvector alpha. Then u star alpha is equals to lambda bar alpha. Then note that S alpha is equals to u plus u star whole alpha. That will be equals to lambda alpha plus lambda bar alpha. That is equals to lambda plus lambda bar whole into alpha. So that means whatever the eigenvalue. Now that this, what is this? This is means the two times real part of lambda. This lambda plus lambda bar is actually two times real part of lambda whole alpha. But this is real part. But lambda mod of lambda is actually has to be 1. So that means that real part of lambda that has to be equals to, for any lambda, that real part of lambda that has to be equals to minus 1 to 1. It can't go beyond 1. So that means minus 2 times less than equals to 2 times of real part of lambda, that is equals to 2. So therefore spectrum is actually spectrum, this eigenvalue actually contained in minus 2 to 2. All of its eigenvalues are real numbers because of the self-adjointness lying in the closed interval minus 2 to 2. This is true. Last options. Let v equals to c2. The operator defined by u x y is equals to this is an unitary operator. Okay, what is the operator u actually defined? I'll just quickly check this one. U x y is equals to, here all the options is correct. Actually, this was the problem of, this are the 4 separate problem of the Hofmann-Kunz. I have 4 separate theorems. I have combined them to form a question. Okay, so what was the questions? I'm not able to see the questions. X plus iy by square root of 2 and ix plus y by square root of 2. So u is a finite dimensional operator. U is actually from C2 to C2. So now u will be unitary. Then by option 1, u is unitary if and only norm of u alpha is equals to norm of alpha for all alpha belongs to the vector space V, which is actually C2. Then we have to check norm of u of xy. This is we have to check. That is equals to norm of x plus iy by 2 with ix plus yi by 2, right? And this is if and only if. This is the if and only if sign. If and only if. So what is norm? So let's take this one. This one will be like x plus iy by 2 with inner product with x plus minus iy by 2 plus x ix plus y by 2 with minus ix plus y by 2. This is the inner product basically. Okay, to take the inner product. So that means it will be like x square minus iy square. Then I square is equals to minus 1. This will be plus y square by 2. Plus this will be like y square minus ix square. That will be plus x square by 2. This is equals to x square plus y square. And that is equals to norm of x and y. Okay. This is what it is. So therefore, u is an unitary operator. Okay. I think it's already exactly 9. So I think it's better to stop here. So do we have any problem? These problems are actually I have tried to give, especially the last one, last problem. This is actually this each of them are actually a good problem. Each of them are a very big problem. I have tried to give try to construct the new problem out of this. So one thing I can assure you that if you are going to give net exam or jam in some day, maybe jam is not, but if you are going to give net exam in some day, questions will be this MSQ questions. There are MSQ questions which are of 4.75 marks. Those questions is going to be this much difficult. So you have to prepare that way. So do you have any other doubt? I know I have made again the singular value decomposition. There I made a mess once again, but I'll try to fix in the notes which I am going to upload. Any other questions regarding the course content or any other doubt, at least except the singular value decomposition last part, not the first part, because that I have to look at carefully. I have not looked at it carefully. Any other problem from the course content? So if there is anything, you can ask me. Otherwise, all the best for your exam if you are going to appear in the exam. And thank you everyone for being with us. And you can give the what is called, you can give feedback. I think there is a feedback form circulated each time. Give feedback whatever you feel. And thank you everyone. And if there is any no doubt, then I will end the session, and as well as um, I mean, this is the last tutorial session and this is the last moment. So thank you everyone and all the best. I hope exam is in this month, maybe around 2021. I don't know exactly the date. Thank you everyone. You can, if you don't have any doubt, you can leave. I will stop in 1 minute.